Okay, so I'll record this so you can have it for your records. When you're studying or preparing, you can always go back and see it in e-class. So, what is welding engineering? Does welding engineering matter? Right? Open questions, and you would not be surprised that people have very different opinions about it. I'll give you mine. And if you have a different opinion, I would love to hear that. You can send me an email and we can have a conversation. But I thought a lot, and this is the way I see welding engineering. Up here. We have welders and we have engineers. And I see an analogy with music. And welding is very, very similar to music. And this analogy seems to be applied so often to so many aspects. So a welder is similar to a musician. And I put here this image of Paganini, who you know, it's a very famous violin player. Was a virtuoso. He was so good at playing violin that when he died, they didn't want to bury him in a Christian cemetery because they said that to play so well, he had to have made a pact with the devil. Crazy stuff, right? But so good he was. And welders are much the same. Welders have like this incredible ear and they listen to the weld and they know what's going on. They have this incredible hand that can make these patterns so precise. And they can control things as they hear them, they can correct them. There is this incredible ability to do something that in the end then is so perfect and pure and beautiful, right? Welders and musicians are very similar in that aspect. Although I haven't heard of any welder that has been refused burial at a Christian cemetery. Now, Paganini, who was a violin virtuoso, needed a violin. One of those he had was made by Antonio Stradivari of Stradivarius violins fame, right? Stradivarius. Now, you might have heard about Stradivarius. You might have heard about how amazing their violins were. If anything, they still play well and they are ridiculously expensive. What nobody says, and by the way, I looked into this, was Stradivarius a good violin player? Chances are he could play a note or two because probably he needed to test the violins. But nobody talks about if he was a good violin player. Now, everybody talks about these violins he made. So the analogy of Stradivarius with the welding engineers is somebody needs to make these machines. When you have this incredible welder making incredible work, they need their Lincoln machines or their Miller machines or whatever machines. Somebody had to have made it. The same person born 100 years ago would not have looked so good. The difference between this amazing person today and the same amazing person 100 years ago is that now it has the machines that can help the welder in their craft. All right, so first important difference, right? When people say, you teach a class on welding and Nate teaches a class on welding. What's the difference? Well, one of the differences is that the guys from Nate are gonna weld a whole lot better than me. Now, I can explain my bad welds a lot better than them, right? And we need both. Without welders, we don't weld. But without the machines, we don't weld either, right? So here you see, this is me in the lab looking at our amazing welds inspired by the muses and the light coming into it. Now, there's another thing the welding engineers do, and that is the equivalent of composing, right? When Paganini would play a piece, could play pieces like by Mozart, right? He had a music sheet that said what not to play, when to play it, how to play it, right? And that was the role of the composer, right? Like Mozart. And the composers will compose these pieces, these symphonies, these concertos, right? In which each note has a place for a reason. And welding engineers also do that when somebody somehow needs to determine how many volts, how many amps, at what velocity, right? With what electrode, right? Much like we tell the welder with the musician what to play and how to play, somehow the welder needs to know what to weld and how to weld. Now, these three roles that I described quite clearly and as quite distinct, very often are merged. Sure enough, Paganini composed his own pieces, and sure enough, Mozart was a virtuoso at the piano too, right? And depending on what we're welding, sometimes the welder already knows what to do. When a guy with a welding truck goes to the field, typically he doesn't go with a welding engineer. This person knows what to weld and how to weld. But if we need to make pressure vessels, if we need to make nuclear equipment, if we need to weld an airplane, trial and error or past experience is not enough because it can be too expensive to try, or we might not have the past experience. So what I'm trying to do here in this slide is to make the difference between what a welder is and what the welder does, and what a welding engineer is and what the welding engineer does. Even though sometimes the responsibilities, they might merge, it's clear that there are two different things. Now, I say all this to some extent as an excuse for my poor welding. This little girl you see here is smiling, that's my daughter. 2 years ago, she had a day of welding training at St. Joe's, and she loved it. She had this day of welding training, but I haven't. So she laughs at me because she says I talk about welding, but she actually knows welding, and yeah, and it's true. But when it comes to explaining the bad welds, yes, I can explain those, huh? and other things. So let's move on. Welding is like an unsung hero. People don't realize welding until things happen. Let's talk about when bad things happen. Here you have an offshore platform that collapsed and killed 123 people, $200 million. And what happened for this platform to collapse? Well, these things measure depth using like a sonar, and they wanted to put this sonar that has to be underwater, and they said, okay, let's weld it to a non-structural member. All right, here you have the legs of the platform, these 5 legs, and you see this crossbar. This was in theory non-structural, and they put this sonar, this hydrophone here. Now there is a problem. As you're going to see and learn in exquisite detail, not everything is welded the same way or with the same materials. And in this case, when they welded steel that looked just as shiny as any other steel, the steel became too hard and too brittle, and eventually it cracked. Just for putting a hydrophone. So this non-load bearing member, when it cracked, you realize that when this cracks, all this leg has essentially like a pivot point, and the leg opened up and the whole platform tilted and collapsed. Just because they put a stupid hydrophone in a non-load-bearing member. Welding matters. If you don't know welding, bad things can happen. And the person who put this here, maybe they thought they knew welding because they could lay down the bead. But in the end, something went very, very wrong. Another example, you might have seen this photo in pretty much every course in materials you have taken. This is a Liberty ship that cracked in half. These ships were made so many to cross the ocean, supplying Europe with supplies from the US. These ships had a particular aspect that they used kind of automotive manufacturing concepts to make them, like, I think the rate was 1 ship per week. And they were making so many of them, and one of the things that enabled them to weld the ships, to make the ships so fast, was welding. But welding wasn't really well understood, and many aspects of metallurgy were not well understood. And what you don't know actually can hurt you, and pretty bad. And these ships were cracking. They were not cracking because of the weld, but the cracks were associated with the welds and pretty poor steel, right? So if you don't know welding, you can die on an offshore platform. You can die in a ship sinking. I read that more of these ships sunk because of structural failure than because of torpedoes. That's a pretty sad thing to say, right? Now, not only, this is what happens when you don't know welding. Let me tell you something that happens when you know welding. After World War I, Germany couldn't have any meaningful army or navy or anything. So there was what it was called the Treaty of Versailles, in which they said when it came to ships, they could make ships only very, very small, kind of a joke of a ship. And before Hitler took power, Germany was abiding by these rules. However, the way the metric for size of a ship was the weight, the tonnage. And the state of the art was riveting the ships. And because the ships were riveted, there was lots of overlap and wasted weight in wasted material in the overlap. In this ship, you see the graph spec. What they did is develop low hydrogen electrodes to weld the ship. Now the ship that was within the constraints of the Treaty of Versailles was as powerful as a normal battleship, right? And it's incredible, but it was still within the constraints of the treaty. When World War II started, these ships started to raid the world, and it was attacking the convoys supplying the English. And the English were desperate, chasing after this one ship. They sent 9 squadrons to 9 parts of the world. Eventually, they found him in the South Atlantic. And one of the squadron had 2 cruisers and a light battleship to go against this one. They cornered it. Eventually, this ship was brought down, but it wasn't sunk. And the sailors went to Montevideo, right across my city, Buenos Aires, and they scuttled the ship. So just think of this. When you don't know welding, you can crash an offshore platform. You can have cracking ships. But when you do know welding, you make a ship that is so powerful that it deserves 9 squadrons around the world chasing after this one ship. So this is for the Germans. Here's another interesting one. This is a T-34 tank. This is the tank that the Russians had during World War II. This tank is famous for many reasons. One of the reasons is that it's the tank that the Russians fielded in the Battle of Kursk, the largest tank battle ever, right? In which it was the T-34s versus the Panzers. in this battle, the kill ratio was 1 Panzer tank would kill 70 34s. You know who won? The Russians won, because they made more than 7-1 T-34s. How could they do this? Well, the Germans were welding their tanks by hand. The Soviets developed the process of submerged arc welding, of which you're going to hear plenty in this class. And with this process of submerged arc welding that is either semi-automatic or automatic, they could weld with very high quality and very high productivity. That was an amazing feat. The guy who led the development of this welding was Professor Patton. And after the war, for having saved the motherland, he was given the highest award of the Soviet Union. And also, he was Ukrainian. He was named the director of science of the director of the Academy of Science of Ukraine. Now, just think of this: was not a quantum physicist, was not a mathematician, was not a biologist or chemist. The director of the Academy of Science was a welding engineer, and because what he did changed the course of the war. So I think welding kind of matters, right? You don't know welding, you kill lots of people. You know welding, and maybe you also kill lots of people, but at least you intended in this case, right? Like you can do things that affect the course of nations. Now, I've been talking about World War II, but more modern times, welding is very involved in aeronautics. For example, an engine has a shaft, and parts of the shaft are cold. This is the front of the engine. Part of the shaft are hot. So you use two different materials, and those two need to be welded. They're welded in solid state. The Airbus 380 that has two floors, this plane could only be made so big. You know why? Because it's welded instead of riveted. And because it's welded instead of riveted, it can be a lot lighter. Funny enough, the people who developed this laser welding for the Airbus 380 were former Soviet engineers from the Patton Welding Institute. The one that developed the welding for the T-34 tank, but after the Berlin Wall fell, many of the top scientists were unemployed or very underemployed. And they went to France and they did this amazing thing, right? Isn't that crazy? Now, when the F-22 was developed and the F-35, they started to weld airplanes. Typically, planes were riveted. And when you weld fighter planes, you use electron beam welding, because typically you make them out of titanium, and titanium is very sensitive to oxygen, so you weld them in vacuum. And if you have a vacuum, you might as well shoot them with an electron beam. So many ways, welding is so essential to make many things. Now, this is a plane that in the end didn't reach full-scale production. But the idea of this plane on the bottom right was to make a jet plane that would have the cost of a propeller plane. And to make this plane cheap enough as a propeller plane, what they did is they adopted techniques of car manufacturing. And among those things was a new way of welding. In this case, it's not welded like a car, it's welded with another solid state process, which we will see later in this class too, called friction stir welding, that can give very good welds and very fast, instead of using rivets, right? Welding enables technologies that are so complex and so radical and so influential. Rockets, you like rockets? I like rockets. And so let me tell you some stories about rockets. The Saturn V, the rocket that was developed to put people on the moon by the end of the decade, by the end of the decade of the 60s, almost failed. There were two problems that took them until the last minute to fail. One of those two problems was that they couldn't weld the second stage. Isn't that amazing? We all almost missed the race to the moon because of welding. And there are articles, and I have uploaded in a supplemental material in the lecture of today, some papers of the time and a paper that I wrote describing some of these stories. External tank of the space shuttle, very interesting. It's aluminum and used to be welded until somebody thought, hey, if I mix aluminum with lithium, lithium is number 3 in the periodic table, it's so light, right? If I mix aluminum with lithium, my aluminum is lighter. And all the weight I save in this tank, I can use it as payload. How smart? Except you cannot weld it then. The first attempt, the first way of welding it was using a plasma process developed in Canada. And then they switched to a solid state process, friction stir welding, which I mentioned about the commercial jet plane, the small jet plane, right? And more things, rocket. You might know that Elon Musk doesn't get along all too well with Jeff Bezos. And in addition to these gigantic egos, what happened is that to make the rockets of SpaceX, as well as to make the rockets of Blue Origin, you need to weld them. And they're welded using friction stir welding. And Jeff Bezos stole the welding engineer from SpaceX. And Elon Musk is not too happy about it. If you read the biography of Elon Musk, they have a couple pages related to this incident. Welding matters. Cars. One of the key obstacles in making cars efficiently is welding them. Now that I mentioned Elon Musk, you know that the Model S and the Model X of Tesla are made of aluminum, and they're essentially made by hand. But the Model 3 is made out of steel, and is meant to be done in the same way you make a Volkswagen car. Super automatic, super high production. Okay, people have been making steel cars since forever, but Tesla wasn't. When they started to make the Model 3, it wasn't welding well. It was a terrible nightmare. And the one reason why the Model 3 was delayed with lots of problems for Tesla is because they had welding problems. Isn't that interesting? Welding again, like everybody knows Tesla and everybody knows Elon Musk and everybody knows that the Model 3 was late. What not everybody knows is that just welding, spot welding, was a problem. Big trucks like we have here in Alberta, those depend on welding completely. Pipelines, I know at least one of the attendants here has been welding these type of things. You know all too well about what this photo means. The boat tower in Calgary, welded. Well, we already talked about offshore rigs, but it's not only war machines, it's not only jets and planes, it's not only pipelines and big things. Look, I took this photo. This photo you see here, I took it. If you remember when I told you I was in charge of a foundry in Colorado, so we would go for field trips with the students to an art foundry. And in this art foundry, what they were making is a horse. And what I learned is that a cast sculpture in reality is a welded sculpture. Who knew? So when people in this case were made a horse, the artist makes a horse and they make the patterns and then they cut them. You see how this is different chunks? And then they're cast little these chunks individually. And then you have to put them together. And you put them together by welding. And you know the crazy thing? The artist made the horse hairs here and here and here. But when they cut it and weld it, welding doesn't come with hairs. There's another guy who comes with a Dremel and makes every hair individually, one by one, so that you would not notice the weld. You realize the challenges of this weld, because not only it has to be a perfect weld, but the chemistry has to be perfect. Because when the bronze oxidizes, you don't want it to oxidize with different colors. And I was in Jasper recently. I forgot what restaurant it is. I think it's Jasper Pizza. They have an aluminum bear, a cast sculpture of an aluminum bear. And you can see the welds, and they did a pretty poor job there. You should go and see. So welding matters, that for sure. And welders and engineers, welding engineers are not the same, but we're symbiotic. We cannot live with each other. Here he said something on the impact of welding, and I'm going to go quickly over that, but the impact of welding is big in money, and it's bigger in Canada than in the US. These notes you have, I uploaded in e-class. So let me tell you briefly a couple of things about welding, because there's a challenge. People say welding is an art. And sure, like playing music is an art, but making violins is not an art, right? And some people say we already know everything we need to know. We've been welding bridges for the last 100 years. Why do we care about welding? Well, let me tell you. Let's take a voyage into the weld. So here we have Joe the welder, or Wesley the welder here. And we all have seen this. And we get closer and we see the welder and the sparks. And if we get even closer, we see what the welder sees. We see the molten metal, that is what we call the weld pool or the weld puddle. We see this bright light that is the what we call the arc. We see an electrode, and there are many types of electrodes, right? But let's go deeper. So this is an image from our lab from a different welding process. But although the welding processes are very different, we see the same thing. We see an electrode. We see the bright light that is an arc, which is a plasma. We realize that the electrode doesn't touch the plate, but electricity flows. Now, there's an interesting question. We have electricity flowing through a gas. Well, you don't see that every day because you go past an electrical outlet and the electricity doesn't jump at you. So there is something special about welding in which the electricity goes through a gas. It's not supposed to. Why? How does electricity go through the gap? Well, the gap has a gas, typically is argon or some gas. And what happens is that in this gas, some electrons are loose, right? And the loose electrons cause electrical conductivity, much the same way in which we have electrical conductivity in a metal. The electrons move and carry electricity. But why do we have loose electrons in our arc? Well, of course, the electrons are loose because it's very hot. The electrons are attached to the atoms, more or less like apples are attached to the apple tree. And if you shake the apple tree hard enough, some apples are going to fall. And temperature is a measure of kinetic energy. So if you increase the temperature enough, you agitate, you shake the atoms so much that some electrons get loose. How hot? Well, the surface of the sun is 6,000 Kelvin, but an arc is 20,000 Kelvin. Now it got interesting because a welder has in their hands something that is about 3 times the temperature of the surface of the sun. That's crazy, but it's true, right? So a welder has something that is hotter than the sun. Not too many places on Earth are as hot as that place when the welder is welding. That's incredible. Is that how you need to be to shake the electrons loose? Now, why is it so hot? Well, if we carry electricity, as the electricity goes, there is a resistance. So we have this resistive heating that creates so much heat, right? And all this comes from the equations. We're not going to be doing these equations in this class, but you start to see how the magic actually obeys things that we know, how this art actually obeys things we know. So the electricity goes, creates this resistance, creates this heat, and the heat is dissipated by a large extent by radiation. So all this intense heat comes out as radiation with a significant ultraviolet component, and that's why we need masks, as you're going to see in the seminar of next week. That's why we need the personal protection equipment, because this energy is a lot. If you weld even for a minute without protection, you end up with a tan that looks as if you had spent the whole day at the beach. And if you weld without protection for more than a few minutes, you get a cancer that looks like you were a worker at Chernobyl, right? This is serious stuff, and that's why welders are very well protected. Now, not only the electricity causes this intense heat, also causes motion, right? And we're going to see how the electromagnetic forces, we're not going to be writing equations, we're going to see how the electricity creates a magnetic field, and as the electricity and the magnetic field interact, they create a pressure, and the pressure creates a jet. And this jet has a velocity, 300 meters per second. It's a typical velocity of the plasma jet. But to give you an idea, a plane, a passenger plane, is more or less 240 meters per second. So how interesting. A welder is welding and is controlling a temperature hotter than the sun and faster than a jet plane. Now, when people say we know everything we need to know about welding, no, we know nothing. It's just a coincidence that for the welding of simple things, the temperature of the sun and the velocity of a jet plane haven't created a disaster. But when we try to weld other materials, disasters do happen, right? And we need to understand. And if we want to be more productive with steel, we need to understand things beyond the miracle that made all this combination of things work in ignorance. To understand, and this here will be my last couple of slides, to understand this combination of electromagnetics and fluid flow that are in the arc, you need to use a field called magnetohydrodynamics, which is an awesome mouthful, right? And the guy who invented this field is Hannes Alf Venn, which was an engineer, and he got developing magnetohydrodynamics, got the Nobel Prize in Physics in 1970. So he was working on the radiation, the magnetohydrodynamics of the sun. Now, we in welding are working on something that is 3 times harder than the sun. I'm waiting for our Nobel Prize. Look, these are photos from my PhD thesis. Whatever they are, which we're going to discuss later, these are really bad welds, and they are the consequence of what happens when the plasma is too fast. And I'm going to skip this, but I'm going to close on this slide for today. That welding is interdisciplinary. So whatever aspect of, every one of us will feel comfortable and in love with an aspect of welding and challenged by some other aspect of welding, whether it's the hands-on, or whether it's the mathematical, or the physics, or the material science. There will be something that will make us happy and something that will put pressure on us. And in this class, we're going to go over all of those very gently. We cannot go too deep, but you'll feel very powerful starting to have an understanding of so many of these different aspects. So I'm going to stop here for today, and thank you very much for attending this class. If you guys want to send me any comments or feedback, I have no way of knowing if I lost all of you or all of you are happy. So will help me get better and better. So I'll stop the recording.